So this is number 4 from 2017. Let's go. So it says, a student investigates various dyes using paper chromatography. The student has samples of 3 pure dyes labeled A, B, and C, and an unknown sample that contains 1 of 3 dyes. Student prepares chromatography chambers shown above on the left by putting a drop of each dye at the indicated position. The chromatography paper, which is polar paper, and standing the paper in a non-polar solvent. The developed chromatograms are shown above on the right. Which dye, A, B, or C, is the least polar? So again, the paper is polar, and the solvent is non-polar. Oh, they say it right there. So which dye is the least polar? Justify your answer in terms of the interactions between the dyes and the solvent, or between the dyes and the paper. So which one? C, A, or B?
B.
Which one is the least polar? So it's either C or B.
I'd say B.
I'd also say B.
What's your justification?
Capillary action works better for polar substances.
Ooh, yeah, that is true. That is true. I will give you that. Or how about this? Capillary action probably works best when the material moving and the mobile phase and the stationary phase like match, so that they like attract. Like polar things attract polar things, non-polar things attract non-polar. So here's the problem. Okay, remember it's asking which one is least polar, meaning it probably is gonna attract to the non-polar solvent the most. So why is C the best answer?
So if you had a polar substance, though, it would probably be the.
If it's polar, what's it going to be more attracted to, the paper or the solvent?
The paper.
It would be attracted to the paper. If it's attracted to the paper, will it travel with the solvent very well then?
No.
So you know that because dye C traveled the best, I'll say best, with a non-polar solvent. That would be the reason, meaning it traveled the furthest. Okay, so so you guys got to remember the like dissolves or attracts. This is weird. So it's different. You know the phrase opposites attract?
Yeah.
Well, in the case of polar versus non-polar, polar things are attracted to polar things. So, and non-polar things are attracted to non-polar. This is exactly like why when you guys are trying to say wash your hands and they're greasy after cooking, or you've used a lot of oil and like kneaded bread and you can't like wash your hands very well, it's because water is very polar and it doesn't do a good job cleaning non-polar things. So like dissolves like. Polar dissolves polar, or non-polar dissolves non-polar, but it has to match in polarity. Okay, and then okay, question B: which dye is present in the unknown sample? Justify your answer.
I'd say dye A.
Correct, because why? Even though this doesn't quite match, there's some reasoning here. Dye A is correct.
Mm-hmm.
And how would you justify it?
It's the most similar.
Yeah. And how come it's a little bit lower than dye A in the standard, right? This is our standard. This is our unknown. Why is dye A a little bit lower?
It might be more pure.
I was gonna say because the solvent front or the paper.
Yeah. So A, how about the ratio of travel is similar to the standard. Now, because do you guys see how let me erase all my lines and stuff. Do you see what percent of the way, if the solvent front is 100% in this case, what percent of the way is dye A up from its starting spot?
Yeah, about
it's about 50%, and then do you guys see in the unknown, it's approximately 50% up the solvent front as well?
Okay, yeah.
Yeah, so they probably want to see something about the ratio. I think, if I remember right, they called that the retention factor. I think when we did our lab with, we did this lab with black dye. We just did a little demo, and then we did the Kool-Aid lab. I think RF is called the retention factor, and that would be our 50%. You don't need to reference the word retention factor. You would just say it traveled about the same proportion. So, and that's it for the question. So that was a really short question on the test. So are you guys okay with chromatography?
Yeah, pretty okay.
Okay.
I just it's a little confusing that like saying non-polar things attract non-polar things.
Yeah.
Because it's very strange to think that a substance that's made up of, let's say, only positive electron or only positive molecules can attract something else positive.
Well, but it's not positive. Polar means there's a positive and a negative.
I said non-polar.
Oh, gotcha. Non-polar. Remember, that's why it's really weird that. Okay, yeah. I guess the non-polar one's a little weirder, but okay. Here's the thing: non-polar, when you talk about vapor pressure. So say I have a liquid.
Yep.
And all these particles are non-polar. Okay, so say it was like hexane, C6H14 hexane. And every little particle, red particle, is a hexane particle, versus you've got a glass of water. Here's a bunch of H2Os. So everything in here is polar. Okay, what's true about the vapor pressure? If I could seal this container, both containers, put a little pressure gauge on here, and we can call this P1 and P2. Okay, what's gonna be and they're both at, let's say, 298 Kelvin, which is room temperature. Which pressure gauge is gonna read higher?
P1, due to the fact that C6H14 is well, what do you mean? Sorry, I'm very tired.
Yeah, no. You're correct.
It'll vaporize.
It'll vaporize. It'll escape the liquid phase more readily because all the little intermolecular forces, I could draw them as yellow lines. All the little, they're weaker, right? Okay. So non-polar things are definitely gonna have a higher vapor pressure because they're less attracted to each other. However, if I introduce something like what would be a good thing, like grease. Grease is probably like C. Oh, what's probably the chain length? Probably 18H 38 or longer. Okay, if I introduce these long grease chains into hexane or into water, what's going to happen? Well, I get these long chains that like attach and dissolve just fine in the hexane, and they intermix, right? But in the water, wouldn't I just end up with a layer of grease on top?
Yeah.
Okay, and it has to do with the fact that these yellow intermolecular forces can form between the green molecules and the red molecules because they're both nonpolar, but they can't form. There's something about the London dispersion forces and the difference in polarity that keeps them from being, the word is called miscible. So here, these are immiscible, okay, the green and the blue, but these are miscible. Okay, miscible means that they have the ability to mix. So the big thing, you just got to remember, like dissolves like. Like that's a key thing and very useful throughout life, because that's why, do you guys know, whenever you get like one of the price tags on something plastic and the price tag doesn't come off and it's all goopy, and you're trying to scrub it off and wipe it off and it's just leaving black, like gummy price tag mess, then you're supposed to actually dissolve it with what? Have you ever used Yeah.
I have never done that.
You've never had like a price tag stick on something shiny and you want to get it off and it just leaves smudges of stickiness?
Oh, you mean that? I thought you meant like clothes or something.
You use
use acetone.
acetone works sometimes, okay, but also a lot. There's stuff called have you ever seen it? It's called like shoe goo.
No.
So shoe goo is made up of like I don't know if it's hexane exactly, but it's got these long non-polar chains in it, and it will dissolve non-polar solvents like non-polar glue stuff. It works really good. So does the stuff that you guys do you guys remember your limonene? Yeah, if you use any cleaners that smell like orange, those cleaners have limonene in it, and limonene is non-polar. So if you're getting something that's goopy that doesn't come off and you try a non-polar solvent on it, a lot of times it'll work because the solvent you're trying to remove or the sticky stuff is non-polar also. So like dissolves like.
So adhesive is non-polar?
Some of it, yes. A lot of tape and things that you would think of as like sticky adhesives are non-polar. Yeah.
Oh, that kind of makes sense why flex tape works underwater.
Yeah, things and hey, does flex tape have kind of an oily smell, almost like gasoline? Does it have
Probably.
So anything that smells kind of like gasoline or solventy, if it doesn't smell like acetone, but it smells more like gasoline, then that is a non-polar adhesive. And if it smells like acetone or if it has no smell, then it's probably a polar solvent and it's probably water soluble. So a lot of water soluble things don't smell, and then a lot of things that are not water soluble, then they have a smell to them.
Makes sense.
Okay.
Water doesn't have a smell, so.
Correct. Okay. Next thing, we're gonna move on. I've got how much time do I have? I've got 15 minutes. Perfect.
Yeah, and of course you started a little late, so.
Yeah. Yep. Okay. Here you go. Student performs an experiment to determine the enthalpy of combustion of 2-propanol, and they give you the formula. So they're burning propanol, which combusts in oxygen according to the equation above. The student heats a sample of water by burning some propanol that is in an alcohol burner, and it's represented below. So that's the little thing with the wick. So that's called a burner. The alcohol burner uses a wick to draw liquid up to the flame. The mass of propanol combusted is determined by weighing the burner before and after. So they just weigh that little bottle before and after, and they can tell how much they've combusted. So do you guys have any questions on the setup?
Yep.
Okay. So data from the experiment are given in the table below. So they combusted 0.55 grams. It heated up 125 grams of water in that beaker. The initial temperature was 22. The final temperature was 51. And the specific heat they give you is the traditional specific heat. So it says calculate the magnitude of heat energy in kilojoules absorbed by the water. Assume that the energy released from the combustion is completely transferred to the water, so it's a perfect calorimeter.
Oh, cool.
Yep. Everything on here will always be a perfect calorimeter. So, okay. So, what equation are you going to use?
Is this MCAT?
Yep. Q is MCAT, and we're gonna do this for the water first. So, if you've got mass of water, 125.
It is in grams.
Yep, and that's in grams. That's perfect because the specific heat of water is also in joules per gram.
Okay.
So then the heat capacity 4.18 joules per gram degrees C. Again, as you're doing this, you just check that your units cancel, and then change in temperature. What's our change in temperature? Like
it's gonna be like
19.
9?
Oh wait, yeah, wait, 19, right?
19? Is it 9?
I think it's 19.1.
I don't know. I'm very tired, so I might.
Okay, but you calculate 19.1 degrees C would be our change in temperature. Oops. And I gotta refer. Let me see if I can find it. I'm a little jumbled. I'll just look at the answer so that I can not calculate it. Yeah, okay, so it comes out to 15,200. So equals 15,200. And what's the units on the answer? What's the units of heat?
Oh, it's in Celsius.
Nope, that's the temperature.
Sorry, joules.
Joules, yep. So you could write your answer like that, and preferably when we deal with enthalpies and heat, it's a good idea to be able to quickly convert to kilojoules. So I'm at 15.2 kilojoules.
Yeah, Mr. Ford?
Yeah.
51.1 minus 22 is 29.1.
Oh, 29, not 19. Thanks.
Yeah, no, it's just, I was like, that is not 19.
No, 29, sorry.
Okay.
And it comes out to 15.2 kilojoules, and this is from their answer, so I know that that's correct. But my subtraction was incorrect. Okay, what's it say? Based on your experimental data, if 1 mole was combusted, how much heat in kilojoules is released? Okay, so here's the thing. Did we combust a full mole?
No.
No, we combusted way less than a mole, and it released that much energy. So the question is, if we did this with a full mole, then how much would it release? So what we have to do is calculate what's called a molar enthalpy or molar heat change. So basically we want to get kilojoules per mole, right? So I just start out and I need to convert 0.55 grams to moles. Oops, 0.55 grams. And then there are, let's see, what was the formula? C3. So C3 is 36 plus there's 8 hydrogens, which is 8. And this is so far that. And then oxygen, there's 1 oxygen, so 16. So I get 0, 12, 20. I get exactly 60.0 grams per 1 mole. Okay, so 0.55 divided by 60 comes out to, oh, they don't give me, I'm going to have to calculate this. I'm solving it differently. They did it all at once. Let's see. 0.55 divided by 60 is 0.00917. Okay, and here's a good reminder. You guys see how many sig figs in their data?
Let's see.
In the 0.55.
Oh,
2.
2.
So when I was using like molar masses, do you guys see that I went down to the 10th place so that I would get 3 sig figs on that?
Mm-hmm.
Okay, so when you're doing intermediate work like the 60, then you're gonna just be 1 digit at least more precise. And then when I wrote down my answer, I wrote down with 3 because this isn't the final answer. Okay, and eventually I will round down to 2. So this would be 0.00917 moles, right? So I need to get kilojoules per mole. So I just take 15.2 kilojoules divided by 0.00917. And because this number was based on 2 sig figs, now is where I would round my answer to 2. So 15.2 divided by 0.00917 moles would be 1657.57, rounded to 2 would just be 1700 kilojoules per mole. Okay, and that matches their answer. They wrote their answer as 1.7 times 10 to the third kilojoules per mole.
Why do a lot of the times they do that? Like they'll write such a basic number, like
yeah,
one time,
like 1700. Typically, I think what I've found in AP, if it's bigger than the hundreds place, sometimes if it's even bigger than the tens place, then they use scientific notation.
Yeah, it was really funny. I was doing the multiple choice questions last night.
Yeah.
And one of them, the answer was 20.
Yeah.
And the answer was in 2 times 10 to the 1.
Yeah, it's
like, what?
Usually you won't see that.
Yeah.
Okay, all those multiple choice questions on the AP I think what they did, AP hired a company to come write those test questions, and I don't think the companies are traditional chemistry teachers or graders, and so they were even more weird format than traditional AP. So I don't know. Chemists, I think any normal chemist, any person who's like working in a lab would just write that as 1700. I think if you get bigger than 1,000, then you might start using scientific notation. And here's the other thing: if you're publishing papers in journals, the journals have their own set of like scientific notation rules, and you just write your articles following their rules. So it depends on your audience. It depends on your audience.
Yeah.
Answer is 1 times 10 to the 0.
Yeah, that would, yes. And somebody who's not familiar with stuff, they would just do that because they're, I don't know, they don't understand what they're doing. But anyways, a grader would accept this answer. Okay, and if you wrote this, then they would for sure mark you down for sig figs. Okay, it says a second student performs the experiment using the same mass of water at the same temperature. However, the student uses an alcohol burner containing propanol that's contaminated with water. Okay, now, first of all, why is water miscible? They use the word right there. Why is water miscible with propanol?
Because they're both polar.
Correct. And how do you know that? How do you know without even drawing its Lewis structure? How do you know that propanol is polar?
The OH group.
Correct. Very good. Very good. And because you have only one OH group, and it can't be symmetric with one. Correct. You see what I mean? Yes.
Yeah.
No. Yeah. You can't have it symmetric. Even if you put the OH group here, and I know it looks. Oops. I know this looks somewhat.
No, you still got
You still got that.
Yeah, you still have a negative region and a more positive region, right? But my guess is propanol. They said it up top. What did he call it? Oh, he called it 2-propanol. Do you guys remember from nomenclature what's the 2 stand for?
That 2
It's on the second carbon.
It's on the second carbon. Yep. If this was carbon 1, 2, 3.
I remember.
Then yeah. So that one. Hey, would you consider 2-propanol or 1-propanol? Which one would be more polar?
1-propanol.
1-propanol is correct because 1-propanol looks like this, and there is a bigger imbalance of charge because the negative is at one end of a molecule. So this would be more polar, and this is still less polar, but it is definitely polar. Okay, so if they had asked this question, which one would you expect to have a higher vapor pressure? Let's say 2-propanol. This is 2-propanol, and this is 1-propanol. Which one would you expect to have a higher vapor pressure?
The 1-propanol.
Incorrect.
Yeah, no, it'd be 2-propanol.
Yeah.
Because the intermolecular forces are weak.
There you go. There you go. Correct. So the less polar one will vaporize easier.
Yeah, I'd imagine that that O does not like being there.
Yep. Okay. And why is it not good to call that 3-propanol?
Because it's not simplified, and also it's the exact same thing.
Correct. Yep. 3-propanol and 1-propanol are the same thing, and so you don't call it 3-propanol. Okay. So going back to the question, they contaminated this 2-propanol, and it has some water. And it says that the difference in mass of the alcohol burner before and after in this experiment, the second student did, is also 0.55 grams. Would you expect the temperature of the water in the beaker that was heated by the burner to be greater than, less than, or equal to the final temperature of the water in the first experiment? So here you have this, and it's still 0.55 grams. You burn 0.55 grams of this mixture.
Okay, so you're burning less of the propanol.
Correct.
So that means that the temperature would most likely be less.
You are correct. That is one response that they accepted. And then you could have also justified it if you were burning propanol. Would all of its energy be going into that beaker's or into the water in the beaker?
Oh no. Water.
It would also be going into doing what to this? So this H2O, you'd have it would be basically vaporizing the water. So you're generating steam in addition to burning your propanol, and generating the steam would heat up the water less because you're vaporizing it. Now here's the kicker. In real life, it might not have much difference because that steam that you generate and burn, it would also go up and condense on the beaker and transfer its energy. So then Keaton's answer is probably the best, where you just say if it's a mixture, you're burning less of the propanol, which will result in less energy released, which causes the water to be cooler. But they accepted both kind of discussions. Either some of your energy is wasted vaporizing water, or you're just physically burning less. Okay. Sorry. That question also seemed fairly straightforward. Do you guys have any questions on it?
No. Not really.
And are you good with the units and everything on the MCAT?
Yes.
Okay.
I have a weird question about some of the multiple choice questions that I did.
Yeah.
So if to make a liquid or like a substance conductive, isn't the rule that if there is a metal in it that it is usually conductive, or even a salt in it, does that make it conductive?
If it's a ionic.
I have to go.
Okay, see Arthur. If it's ionic and you're dissolving it in water, then it will be conductive.
Okay.
If it's just salt crystals and it's not dissolved.
Oh, yeah, I'm just saying. Yeah. I'm saying substance like solid, like sodium nitrate or.
Okay, yeah, sodium nitrate. Are you talking solid or dissolved?
Dissolved.
Okay, then that will conduct electricity. It won't be magnetic, but it will conduct. It will conduct electricity.
Okay. Yeah, because on chapter 7, there's so many questions. Like literally, like the last 10 questions were all about that. I'm like, what?
Interesting. Yeah, I haven't looked at all of them. I'm gonna look through your guys' results and see.
I feel like I got them correct though.
It'll tell you.
I mean, it's pretty self-explanatory. Like if it's ionic, if there's a metal in it, it's most likely conducts electricity, right?
Yeah, because the definition of electricity or electric current is the flow of not electrons, the flow of charge. Because right, like if you have sodium chloride dissolved in water, then what's flowing is actually the Na plus and the Cl minus. Those are moving to create the circuit. So you don't have to have electrons. You have to have the flow of charge. It could be electron. It could be an ion.
Oh, so it has to have a positive and negative.
Correct.
Correct.
Okay. So like that's why when we put sugar, you dissolve sugar into water. Sugar is like glucose or sucrose, C6H12O6. Well, hey, that's neutral. The overall charge on that thing is neutral. Even though it dissolves and it can be aqueous, it would not conduct electricity.
Oh wait, does that mean acid conducts electricity?
Say that again.
Does acid conduct electricity?
Yes, because acid. Okay. Well, hey, careful. A strong acid will conduct electricity better than a weak acid.
Yeah, that makes sense.
Because there's more H plus and conjugate base, B minus, for a strong acid because it fully breaks apart. If you have a really weak acid, like extremely weak acid, where it likes to stay together, like as HB, and not dissociate, then it will not conduct electricity very well.
Oh, and that makes sense. Oh, okay.
And hey, here's the other thing. If you have pure water, I don't know why it's so small. Let me zoom in. If you have H2O, oh geez, my pen is dying. H2O. You remember this, right?
Yeah.
Or actually, it's probably written better like this.
You're showing the. Okay.
Yeah. So hey, will water conduct electricity?
Yes.
No.
Oh.
What's this K value 10 to the minus 14
Oh,
mean?
it's very small.
Yeah,
It means
meaning it
H2O
stays on this side, right? And hey, is there any charge on this side of the equation?
Oh no, because they balance out.
Correct.
Well, I mean,
this is neutral.
Okay.
H2O has a charge. Oops, because it's a neutral molecule, it has a charge of 0, right?
Okay.
Because most of the stuff in your cup of water is neutral, then it can't conduct electricity. So pure water, this K value is so small, electricity can't flow through that. It won't flow through these particles because there's not enough of them.
Okay.
Now, if you add a drop of acid, or if you add a couple, like say you pour it out of your faucet, what ions are present in your tap water?
Hopefully not lead, but that's
Correct.
One of the
Hopefully not lead. Hopefully just this one, Fe2 plus, Fe3 plus.
Well, also copper, small amounts of copper.
Small amounts of copper, very little metal. Actually, the more common ones would be calcium, sodium, chlorides, because we put chlorine in our water. So these ones are probably, and phosphates, PO4, 3 minus. Those ones are probably the most common. And because those are present, tap water conducts electricity.
Oh, but pure
H2O doesn't. Because the K value is too small.
You know, I remember when I was little, I would always tell people that, funny enough, if you get a pure cup of water, it will not conduct electricity.
Correct.
It won't shock you.
Correct.
And then people would be like, "How is that possible?" And I'm like, "I have no clue."
Well, now you know. Now you know. There's not enough charge.
Okay.
So.
All right. Well, thank you for.
Yep. I'll see you Friday. I'll get you guys feedback. I'm basically gonna create some more questions on AP Classroom. I'll get those out to you today or tomorrow.
Is today Wednesday?
Today's Wednesday.
Why Friday then? Are we not meeting
We're not gonna meet tomorrow. I've got to change it just because I'm doing too much in my other classes. So we're just officially between here and the end of the year. We're just gonna meet, or till the AP test at least. We're gonna meet Monday, Wednesday, Friday.
Then after the AP test?
I don't. Yeah, after the AP test, we'll set up. Hopefully we can do something to celebrate. We'll see. We're gonna definitely have a virtual field trip of Dino, and have the plant chemist talk, and we'll do some interesting things, but it won't be 3 days a week for sure.
Yeah, funny fact actually, I think it's today. Yeah, Oregon State's gonna have a Zoom call with a bunch of new students, and I'm gonna join, and I'm going to see what's up.
Nice. Have fun.
I shall. Hopefully it won't get raided.
Yeah.
Because did you hear what happened during the Zoom call for the senior class meeting?
No, how'd that go?
Oh, it was really, really great.
What happened?
So, a bunch, or like not a bunch, but like at least 4 different dudes came in and just started screaming a bunch of really, really bad things.
Yeah.
Like really bad.
And it wasn't people in our senior class, was it?
No, it was some random British people. I don't know.
Huh. That's
strong British accent.
That's no good.
Yeah. Someone leaked the code.
Yeah, that's no good.
Yeah.
All right. Well, then hopefully that doesn't happen at OSU.
Yeah, I don't think it will, because they sent out an email, and also like these people know if they get found out that they did, that they're not going to be able to go to college. So.
Gotcha.
Yeah. Get banned.
Yep.
Anyways.
Okay. All right. Talk to you later. All right.
Bye.
Bye.